Susan, piezoelectric materials are known since way back.
Yes.
19th century.
Yes.
The end of 19th century. But they're still a hot research topic. How's that?
Well, they're becoming increasingly used in a wide variety of industrial products. Almost every baby that's born now had medical imaging done, usually ultrasonic imaging. The key materials that make the sound waves and then that listen for the echoes are all piezoelectric materials. And so that's one of the large research areas in the field. And then there's a lot of fun new things that are coming up. For example, for energy harvesters. So probably you have heard about the Internet of Things. And if the Internet of Things is going to happen, we have some choices. We can either change batteries for every device that is everywhere, every time a battery needs to be changed, or we can figure out how to harvest energy locally. And if you look at the available ways of harvesting energy, the sun is a great way to do this. Inside, there may not be so much sunlight, and so people are very interested in using mechanical vibrations, which you convert to electrical energy with the piezoelectric materials. And so there's many, many new applications that are coming up now that are continuing to provoke research in the area.
What are the sectors, the industrial sectors, that might be more influenced by piezoelectrics, MEMS, micro-electromechanical systems?
Okay. There's many potential areas where this will be technologically important. This is a very new field. And so what we're seeing is that only now are the foundries, the laboratories where these are being made into devices, only now are those being developed. Among the current industrial products are inertial navigation systems for automobiles. And so there's commercial products from Japan in that area. Ones that I expect could also potentially be interesting. There's a number of optical applications that I think will be very useful to be able to do very high precision optical surfaces, to make surfaces very flat, to be able to change them so that you can control light propagation through a system. That's an area that I expect could be important. There's a huge interest in being able to make infrared imaging systems for night vision to improve driver safety. Many of those materials will essentially be the same family of materials that are used in piezoelectric microelectromechanical systems. And I expect that there will also be a number of medical applications. One of the challenges, certainly in the United States, is that the average diameter of the American is growing. So people become fat. And as people become fat, we're actually losing whole modalities of imaging for medical imaging applications. So for example, when they want to detect ailments of the liver, they try and put an ultrasound transducer up under the ribs. Fat is acoustically attenuating, so you can't see through too much fat. And as people become fatter, we literally cannot see what we need to see. And so there's a huge interest in being able to take a transducer, which is often this diameter, often with a cable that may be rather large coming from the back of it, connected to a box of electronics this big, and being able to take that whole system and make it small enough, for example, that you could put it in a pill and swallow it. And now you could do all of the investigations from the inside perhaps in your doctor's office, and it would be significantly safer and would open up whole new areas of medical imaging we don't have. So that's an area I expect will come. That one's at the very early days, so it will probably be several years before that one becomes commercially viable.
Do the undergraduate students know about the potential of this field? How do you attract young talent to your field?
I find that very often if you can tell someone a story, you can engage their interest. And an excellent example of this, my thesis advisor for my Ph.D. was the man who invented what is now the modern ultrasound transducer. And he was trained as a geologist. He studied rocks. And he moved from a study of quartz to a study of piezoelectricity, and he knew every crystal structure, all of them. He knew the names and chemical formulas of all minerals. And he almost always knew their crystal structure. And he used that baseline knowledge to be able to engineer materials. And so he looked at a material that's largely a useless material, antimony sulfoiodide, and he said, this is interesting. It's connected very beautifully in one direction. It's connected very poorly laterally, so that I can make this motion without making this motion. And that turns out to be essential if you want to make a good medical ultrasound systems. Most materials, when they expand and contract this way, make the opposite motion this way. And so he looked at it, and he said, how can I artificially make a material that will behave like this mineral? And so he decided to make piezoelectric composites, where he took piezoelectric materials and he allied them with polymers. And that became the basis of what is now used in almost all medical ultrasound transducers. And he told a story near the end of his life of being asked to go to an American Heart Association meeting. And at this American Heart Association meeting, they had many medical doctors and thousands of people whose lives he'd saved indirectly because he developed this transducer. And that's the kind of story when you can say, look, understanding what seems maybe like esoteric, fundamental material science can change lives, can save lives. That's the kind of things that makes people interested in maybe giving this a try. Yeah.
That's nice. Beautiful story. Beautiful story, yeah.
Yeah.
Because sometimes we think of scientists of just they're in their labs not caring, but maybe that's not true. Maybe it's never been true.
Yeah, I think it's probably not true. I think most people love to see what they do turned into something of value. And if you can do good for people, that's its own motivation.